All right, thank you very much for that introduction, Grace. All right, thank you. I'll just introduce the title of my speech again. CalAlSil Feldspar Polymers, sustainable nanomaterials that replace cement, concrete, bricks, and composites. I've had a few iterations of my scientific terminology that I tend to use. I've tried the word geomer, which is a hybrid term to describe a geological polymer. I've landed on Feldspar Polymers because that is really the essence of what I've created. It's an alkali silicate and an alkali aluminate, and together an alkali aluminosilicate that then binds together in a structured manner. And I'll show you a few slides that will indicate just the type of structures that we've been able to accomplish. Just next slide. Here we are. Okay. So non-combustible resins, let's begin there. The ceramic and then hybrid ceramic polymers are essentially the most economically viable foundation material for use in construction, infrastructure, energy collection and storage, in particular battery systems that are being developed. So the family of materials that my invention comes into is essentially the structure that you put a battery in, so a battery case. That's the classic use of it. For a number of highly durable requirements for things like transport and main roads, clients, they're looking for batteries that are effectively indestructible, as well as can perform in all types of different environments. So part of the problem that we have in terms of landing a battery and putting it out in what we term in Australia the outback is the extremes in temperatures, both hot and cold, in our desert-like conditions in the outback. So what's required is a very high thermally insulating material, as well as a traditional insulator. So CalAlSil silicate resins, the first silicate hydrogels, which is the beginning of the process to create a silicate resin, is extremely high in thermal insulation or thermal mass. And that's essentially just due to the fact that up to 50%, somewhere between 44 and 50% of the material is water. So this is reasonably unique in the sense that there's not too many gels or hydrogels in the marketplace that are made from a ceramic that don't burn, that don't even char in a fire event, that is available to be deployed in an outback region or a desert style region. I just make the point in this slide that a perovskite calcium silicate, or particularly perovskite, which is calcium titanate, photovoltaic systems are the most likely high volume energy collection system, having the less embodied energy than the silicon photovoltaic cells. I'm sure now we've been around for long enough to realize that we have a supply chain glitch in the deployment of renewable energy solutions, and primarily that surrounds the fact that we cannot manufacture the silicon photovoltaic cells at large enough volumes to really meet the need of transferring all fossil fuel use into a much more localized collection of collection of solar energy through photovoltaics. So really what we're looking at is the likelihood that concentrated solar will be the predominant large collection of solar energy. Of course, wind and other forms of energy will be, in the mix, but we're talking about, something that's replacing fossil fuels. And I do note the very good graphs that were given by Professor Evers last night in day one of this conference, where it was very clear that the incredibly high use of fossil fuels over the past 100 years in particular has made this task of transferring to renewable energy that much more difficult. So we really need to find something that is so ubiquitously obtainable in our world that that you can make these concentrated solar panels from, and a aluminosilicate is the most likely candidate. So essentially, I've written a figure here of 60% of the embodied energy compared to concrete or fired clay. Some of my mixtures have been down as low as 45%. Typically, the non-combustible mixture averages at approximately 50 to 60% of the embodied energy. So it's a big step. Obviously, it's not zero, because when you're comparing ceramic to ceramic, I still need to activate the aluminosilicate system, much like we do in geopolymers. So I guess maybe the first question to answer there is, what's so different between what I've done and what the geopolymer fraternity has done since 1978? The primary difference is that I begin with a silicate resin. That resin is essentially a hydrolytic finder of particles, and allows the particles to coalesce together in a much more ordered and much more structured manner. This allows for higher strengths just through simple evaporation of the solvent, which in this case is water. Finally, the point that CalAlSil wood composites obviously can be made to be carbon neutral, but I guess I'm moving away from carbon technology or carbon rhetoric in my business at the moment. I'm really talking about the actual energy that's used to make these materials and how much energy is saved by making these, as opposed to, or using the CalAlSil resins as opposed to cement. In Australia, just a little bit of context, fired clay bricks manufacturing effectively collapsed from 2007, particularly here in Brisbane, Queensland. And that was simply due to the fact that Australia typically allowed its local manufacturing to use the gas that was locally available, and that price of gas was approximately 40% of what the global price of gas was. So when in 2007 the Australian government decided to tag the price of gas that local manufacturers used to the global price, this made fired clay brick manufacturing very, very difficult in its current form. And I might make the point that this is a 5,000-year-old technology, albeit the fully automated version of the technology is perhaps only about 60 to 70 years of age. But this collapsed in a developed nation. Now, at the moment, for many of you who aren't aware, Australia imports much of its cement powder from Malaysia and sometimes China. But Southeast Asia is a predominant producer of Australia's cement powder, Portland cement powder. So fired clay bricks just simply aren't being used as much. We've still got a couple of kilns running, but not nearly as much as what we used to have. Essentially, the chemistry that underpins the hydrogel, or the alkali silicate gels, as I've written it here, are essentially unsaturated acids. So I use them as a catalyst to order the silicate materials or silicate oligomers in the water solution. Now, this obviously is very difficult to identify, and I'll go through some things that we have identified, but nanostructures in water are very, very difficult to identify using any of the chemical or spectrometric techniques that we have. Essentially, when you start adding in many different components to a system, it makes it almost impossible. So I'll get to that just in a moment. The hybrid resins, so I use, natural rubber, cellulose, silk wool, also polyethylene glycol, polypropylene glycol, polylactic acid, and polyoxymethylene. So essentially polyurethanes are also excellent hybrid polymers. So really I could go down to the local hardware store, grab a varnish, a timber bar varnish, and mix it in with my CalAlSil resins. And suddenly I've got a product that, because the organic component's far, far less than 50%, maximum component I've got up to is 30% of the solid, not of the, it's about 60% solid, 40% water, 65% solid, 35% water, sorry. So that's the 30% of the solid is organic. It simply just cannot hold a flame. So it's by design fireproof. So just trying to give a quick overview of the chemistry. Sodium and illuminates, sodium hydroxide, sodium illuminates, and then silicon or silicic acid, as it's drawn in these oligomers here. They form numerous different oligomers within the structure of water, and they can form these oligomers using a variety of different manufacturing techniques depending on how the water glass or sodium silicate was begun, and similarly how the sodium aluminate began its life. Generally speaking, the higher amount of mixing that you apply to the solution with the higher spin velocity, then the smaller the oligomers become. Just skipped over one there. So the interfacial, this is some of the newer work that I had done over summer. Secondary building units can be macropolymers, like I've explained, ceramic organic frameworks, metal organic frameworks, latex, and mixed inorganic, so zeolite organic frameworks effectively. Now, believe it or not, just simply by painting the resin out, and this is compared to, say, a cement paste. If you just get Portland cement, add the correct amount of water, which is usually 66% of the amount of mass of cement that you've got, then you get a Mohs hardness of around about 2 to 3 for Portland cement. The hardness of a concrete comes from the fact that cement crystals grow into the aggregates. That's how concrete becomes very strong and hard. In this situation, CalAlSil resins, we're working backwards, where we've got water that needs to be evaporated, and I've got unreacted particles in the mixture that then react during the evaporation process, thereby leading to significant bonding at the nanoscale and chemical scale. So just quickly, these images here, just a scanning electron microscope image of some of the glass fiber where I've got my cursor over. A little bit more higher magnification. You can see the 50 micron scale there. Obviously, these particles, I add in these particles, they're very small to begin with as raw materials. They mix around, and it's just simply due to that evaporation that these balls of materials end up being agglomerated. And you have sharing of these balls, and that's essentially the bonding. So very high magnification here. Just indicates the blurriness. You're talking about 5 microns. These are typically silica fume particles, and they typically, even at the scanning electron microscope vacuum, they still retain some water, so the blurriness comes out in the image. This is just an indication of the glass fiber, how the glass fiber looks under the microscope in comparison to the CalAlSil agglomerate at the macro and micro scale. And it's very clear that the glass fiber is, much more of a chemically bound material, solid material, not too many breaks in continuity there. So I just might make the point at this juncture to say that these images are from non-combustible CalAlSil resins, meaning I have not put any organic hybridization in them whatsoever. Obviously, with the hybridization, you get a lot better bonding. Okay. So I just make the point that with the non-combustible ceramics, it's easy to infuse metal particles in them, and then burn them into high temperatures if you wanted to make a cermet, which those cermet materials have some specialist applications. So this is just an energy dispersive X-ray spectroscopy, EDS, of one of these images. This EDS on the right-hand side where my cursor is an EDX of generally the entire image. It indicates you've got oxygen, sodium, a little bit of magnesium, not much, aluminium silica, tiny bit of potassium, calcium titanate, and a bit of iron. Now those components all come from the fly ash that's in the mixture. The aluminosilicate is from the fly ash, and I also have particles of aluminium oxide, silicon dioxide. Okay, so where this dark spot is here, we took a much, basically where the box is, and found out that it's effectively an aluminosilicate with a little bit of the fly ash style materials in it, much higher aluminium peak in that. This spherical bright ball here is, albeit some of the fly ash behind it was obtained in the EDX measurement, but it's basically silicon and oxygen. The aluminium is far, far less in terms of quantity, and it would generally be a sodium silicate. There's a fair bit of sodium there in comparison to the aluminium, so there's not much fly ash there at all. So essentially, you can start to target these little areas in the mixture and actually get some reasonable chemical information out of the scanning electron micrograph. Just give a very brief overview there. Essentially, I've got a list of properties that the ceramic, particularly the hybridized ceramic resins, provide: fast drying, non-toxic, because I can use natural polymers to hybridize with them; flame and fireproof, without a doubt; slip resistant, because they are a ceramic. So once they're set, and they do need to be set, they're relatively slip resistant even when water's added to them. Resist algae and mold. That's because of the, I can add some borax to it. I can also add some, well, the sodium hydroxide itself is also a key component to reducing algae and mold accumulating on these coatings. Simple to apply. This is the key reason we need a ceramic resin in our economy, because concrete is a two-pack process. Asphalt concrete is a two-pack process, or it's a one-pack with a very large amount of energy, so that the paver tends to apply asphaltic concrete at approximately 80 degrees Celsius. But for the general population, for large-scale production of concentrated solar collectors, for large-scale manufacturing of battery cases, we need a material that is easy to apply. It's very important. Zero volatile organic component. That's particularly the non-combustible resin. The hybrid resins have a slight bit of solvent from the organic polymers. Corrosion resistant. Obviously, the hybrid polymers are far more corrosion resistant because I do get liquid seal, and if I get the 150% binder quotient, so I get 3 parts organic binder to 2 parts ceramic binder, I tend to get a product that is in fact air resistant as well, air sealed. So that's quite an accomplishment with a ceramic. As you can see, the particles just really coalesce. Obviously, with chemical resistance, you've got aluminosilicates, very good at chemical resistance. I can make a white paint. I haven't got an image of a white paint here, but they're just more expensive because I can't use fly ash, and no fly ashes are purely white. Essentially, it's just an aluminosilicate with a little bit of borax added to it and a few other components, the calcium hydroxide, for instance. Excellent adhesion. The beauty of the product is the fact that it has excellent adhesion to many things, particularly wood. This is where my anticipation is. I have some high-end clients at the moment who are looking for battery cases, and that's where some specialty equipment giving nice profit style products can be made, particularly those are glass fiber reinforced CalAlSil resins. But there's also many green construction companies in Australia who are interested in the green opportunity to add wood to a ceramic resin to produce a fireproof and potentially floodproof product that you can make houses and commercial construction from, while storing some of the wood waste that we have in abundance here in Australia, particularly in the cities where we're highly urbanised. So there's a mass balance component to our economy, and our current supply chain disruptions due to both COVID and unfortunately the circumstances in Europe are testing those supply chains, the resilience of those supply chains, and realistically, I think we've really established as an academic group that we need to move to a more regionalised production facility of our most foundational and fundamental materials, and it also just makes a lot more sense to have very nimble, small-scale, light industrial manufacturing components, particularly in a developed nation where we don't want dirty, smelly, huge, smoke-riddled manufacturing plants anymore. This is the environmental constraints in Australia and many countries as well in Europe and the United States and North America in particular, essentially very, very difficult to have what we would commonly call a very large volume manufacturing plant. So essentially, just to give you the full picture, the complete life cycle really just relies on clay at the bottom of our feet as the raw material, and sodium chloride, which we extract from the ocean. Now in Australia, we have dotted plants around the nation that extracts sodium chloride for obviously our table salt use, but it's a commonly extracted salt for animal feed as well in Australia. So these things are already occurring. Clay manufacture or clay extraction's very simple. You just get rid of the overburden on a site, which is usually maximum 2 to 5 meters deep, and then you hit clay. So this is the case outside of the desert areas of the world in North Africa, for instance, and the very cold regions of the world in the Arctic and the Antarctic, where material is just so abundant that really just makes sense to move into this chemical regime. And hopefully, fingers crossed, the 21st century becomes the century of chemists, as opposed to the mathematicians who had, I believe, the 19th century, and the physicists certainly owned the 20th century. So I'll just leave it there. I think I've probably gone a little bit over time. So thank you very much, everyone, for listening, and happy to answer any questions that you might